Yeah, for those who don't know me, my name is Weikang Ma. I'm the Beamline scientist at BioCAT, responsible for the muscle fiber diffraction. So, like Tom said, the main improvement for the beam is the smaller horizontal beam size. So traditionally, because the horizontal size is much bigger, so if we want to see the traditional muscle X-ray experiment was done by putting the muscle vertically, because there's a lot of very crowded reflections near meridianal. We want better resolution. But with the new beam source, it's more symmetrical, so it doesn't matter whether it's horizontal and vertical. Most of our current setup, or most of the lab doing things horizontally, so it makes things easier to operate. So another recent improvement we had is the Eiger 9M detector. So Tom liked to see that for over 25 years of his career, finally he got his first fiber detector that is as much smaller pixel size and high frame rate. And most importantly, has almost zero dead time. So even the previous plotters can do 500 hertz. It takes 1 millisecond on and 1 millisecond off. So with this detector, basically we can double the flux at the same rate. And also it's big enough that we can pretty much accommodate all the different modality of the experiment, use a single lens camera. When we had the smaller plotters, if we want to look at higher angle, we need to build a shorter camera. We want to look at the low angle, we need a longer camera. Now with this, we can pretty much get everything we want from a 3 meter or 4.5 meter camera. And another recent development is we found out we can simply dunk the pig heart muscle into liquid nitrogen and then take them out, and the structure seems preserved pretty well. So we did X-ray and the EM to show that it's, of course, fresh one always the best, but the structure was preserved pretty comparable. So after 1 month in -18 or 18 months in -88, the structure looks pretty good. And then we look at how the cryopreserved human heart looks like. So it's look like so most of the tissue in the heart bank, it's all frozen. It's almost impossible to get fresh one. So, and we look at how the non-heart failure patient and heart failure patient, how the overall structure. So we published the first paper, basically just take a first crack of these things, and we are working on with different groups to study this more. So basically, given the availability of the tissue bank, so we expect that this is something we're gonna look at in near future, or we are looking at right now. So for the future plan for this, we want to further optimize how to preserve skeletal muscle. So we collect some pattern from fresh and frozen. It looks pretty good, so, but there are some issues we need to further optimize. And then we need to redesign the BSL2 muscle setup. So this is the BSL2. So for in Eiger, anything that is the BSL2 need to be performed in a sealed chamber. So it's a little bit more stringent than academic lab. So we need to put the muscle in between the two hooks and cover this small chamber. We can do solution change, use this solution change part. But this way, it's almost impossible to measure physiology, measure force, or like doing lens change. So we can do lens change slowly, but not anything quick. So we're gonna do a total redesign and to fit the force transducer and the motor in the whole systems. And then in last couple of rounds, we have been just put 2 regular muscle setup in parallel. So we can just slide back and forth. I don't know why we didn't do this before, but it's very handy. So basically, for this one, we have 2 rigs in parallel. We cut the experimental time in half, mostly for drug incubation. A lot of experiment we done doing drug incubation take about 20, 30 minutes to incubate. So we can basically set up 4, even This is 2. We have another rig, have 4 rigs, so we can set as many as we want, depending on the incubation time. So we can I'm gonna totally redesign all of this, make it much smaller, so we can put in as many as we want. So another thing that couple of years ago, I basically take a whole red heart and just did a pretty rudimentic Langendorf experiment. So hand the whole heart in front of the beam and just scan the heart, and I got pretty not bad X-ray diffraction. So basically, so this will allow us to determine the nanometer scale structure information, and in the same time we can do all the classic whole heart physiology on it. So it enables us to look at the heart muscle from skinned to intact to whole heart level. So right before the pandemic hit, we got this commercial EMK Langendorf setup. So it's we have been doing it slowly. So basically, we designed a setup that can fit in the beamline. So and we collect some patterns. The initial result looks good. The only thing we still need some further improvement, optimize. So this is gonna be we're gonna do this in next couple of rounds and all the way to the APS dark period. So it will be fully operational by the APS-U, by the annual APS-U. Another recent development is Muscle X. So Muscle X is a program that can doing all the data analysis for muscle X-ray or fiber and fiber diffraction. So basically, traditionally, muscle X-ray is kind of only limited to a couple of expert groups in each generation. Now with this program, non-expert can use it and analyze their data. So we want to have a true user, the general user program that the user can just apply beam time, do the experiment, and take their data back and do their own analysis. And also it's greatly reduced the lag time from experiment to publication. It used to take about years to get one set of data to analyze. Now I can train my student to do that in a matter of a couple of weeks. So the further plan for Muscle X is Tom just got his R01 funded that we did to further develop Muscle X. So we're gonna have Muscle X 2.0, basically continue to develop and implement or debug the current Muscle X system. And another part is called the Musical X. Musical X use this musical package to predict X-ray pattern. So basically the goal is to develop a forward program approach, try to interpret X-ray patterns. And we hope it will be a hypothesis generating tools. So that's about it for fiber diffraction.